Okay, I want to thank Diego and Pablo for organizing this wonderful event. And also it's really my great pleasure to be here to present my recent work. So my talk will be closely related to what Andrew just talked about, and also related to what Renee just commented after Andrew's talk. So I will talk about robust matrix completion by nonsmooth Riemannian optimization. So basically, we target to solve this robust matrix completion problem, and we provide a new model for this robust matrix completion problem. More specifically, we model this problem as a Riemannian optimization problem with nonsmooth objective function. And numerically, excuse me, numerically, so Riemannian optimization problem with nonsmooth objective functions can be very challenging to solve. In this work, we propose a new algorithm called a Manifold Proximal gradient method to solve this kind of problem. So this is a, excuse me, so this is a joint work with my student Minghui Huang and my colleague Li-Feng Lai at UC Davis. All right, so let's start with robust PCA. So in robust PCA, we're given a matrix M, and we want to find a decomposition M equal to L plus S, where we require L to be a low rank matrix and S to be a sparse matrix, right? So we know that. So this is a classical problem. And one way to model this problem is to model it as a convex optimization problem. So here, this is one of the convex models. Here we want to minimize the nuclear norm of the matrix L plus the L1 norm of the matrix S subject to this constraint. So here again, M is given. L and S, they are unknown variables. This nuclear norm of L is defined as the sum of the singular values, and the L1 norm is defined as the sum of the absolute value of the entries. Okay, it is known that this nuclear norm can promote the low rankness of the matrix, and the L1 norm can promote the sparsity of the matrix. So very naturally, by minimizing this nuclear norm plus the L1 norm, we can promote the low rankness of L and the sparsity of S. And this robust PCA problem found many important applications in the areas like computer vision, recommendation systems, medical imaging, and so on. Okay, so now what is robust matrix completion? Basically, robust matrix completion is actually robust PCA, where we only have a subset of observations for the matrix M. So basically, we are only given a subset of the entrance Mij for the Ij in the subset, the index subset omega. And still, we want to do this low rank plus sparse decomposition. All right. So very naturally, this problem can be formulated as this one. So again, this is a convex model. Okay. So in the literature, I found that these people usually call this robust matrix completion problem. So I use RMC to denote this convex model. So in this formulation, we can see that again, we're minimizing the nuclear norm of L and plus the L1 norm of S, okay, subject to some linear constraints. And this operator P sub omega denotes a projection operation onto the index set omega. So basically, it requires that this matrix and this matrix, they agree with each other for the components on the index set omega. Okay. And when this parameter gamma equal to 0, we know that this problem just reduced to the original matrix completion problem that we know like 10 years ago. Okay. So when gamma equal to 0, then we know that we're minimizing the nuclear norm of L subject to this constraint. So this is the matrix completion problem. All right. Okay. So as you can see, in all these convex optimization models, we usually have a nuclear norm, right? So the nuclear norm is defined as the sum of the singular values of the matrix. So usually the algorithms for solving this kind of convex models, they need a singular value decomposition in every iteration. So for example, if you want to compute the proximal mapping of this nuclear norm function, then you need to do a singular value decomposition. All right. So that can be very expensive if you do that in every iteration. Right. Okay. So as Renee just commented, right? So there exist non-convex models for matrix completion and also robust PCA, where the non-convex model is usually based on this low rank factorization idea. So for the low rank matrix L, we can do a low rank factorization. So we factorize L to the multiplication of U and V, and the U and V, they are two smaller matrices. Okay, so L here, the size is M by N. Now we factorize that as U times V. U is M by R, and V is R by N. And we choose R to be much smaller than M and N. Okay, so here, this kind of idea was already used in many works. So for example, the very recent work by Rene and his co-authors, they considered this robust matrix recovery problem, where you have a low rank matrix L, and you have some observation to this matrix L. Here, this A is a linear operator. A is known. Okay, and then you have some sparse noise, and Y is your observation. So A and Y are known, and you want to recover this low rank matrix L and also the sparse noise S. Okay, so they formulate this problem in this way. So basically, you minimize Y minus A of U times V. So that means you replace L by U times V. So that's a low rank factorization. And you minimize the L1 norm of this vector to promote the sparsity of this S. All right. So in the paper, they proposed to use the subgradient method to solve this problem. They also proposed another variant of this model, in which you add a regularization term to this model, where you can propose you can prove some very nice theoretical properties. Okay. So the reason to use this subgradient method is because the objective function is non-smooth. Right. So actually, this low rank factorization idea actually goes back to some more earlier works. So for example, this method called L method, it models the following non-convex robust PCA problem. So let's see. So here, I use Z as a approximation to the low rank matrix L. So then I just decompose this low rank matrix Z as the factorization, right? So U times V. And then for this part, so Z minus M, so that will be the sparse part. And then I minimize the L1 norm of this sparse matrix. Okay. So the authors in this work, they propose this L method algorithm, which is actually a non-convex ADMM algorithm for solving this problem. Okay. However, we know that the convergence property of the non-convex ADMM is still not very well understood. Okay. And also another issue about this model is that the optimal solution is not unique. So for example, if U hat V hat is optimal, then we can easily see that this is also optimal for any invertible matrix Q. Okay, because we only care about the multiplication of U and V. Okay. Okay. So to overcome this issue, I mean the uniqueness of the solution. Okay. So one way to handle this issue is to impose some Riemannian constraints to one of the factors. So for example, now let's just look at the matrix completion problem first. For example, in this work by Dai et al., they propose this SET, the set model. Okay, so in this model, they consider the matrix completion problem. So then basically you want to minimize the error between the low rank matrix and the given matrix. All right. So here they impose one Riemannian constraint to one of the factors. Okay. Now let me just explain these notions. So this notion, it denotes the Grassmann manifold. It is the set of R-dimensional vector subspaces of Rm. So this notation, this U here, this is a subspace. Okay, and here in the objective function, we use a matrix U. So what is the matrix U? This matrix U is an orthonormal basis of this subspace. Okay, so these are the explanations to these notions. All right. So now for this problem, we can see that this is a minimization and then minimization problem. Right? We can see that the inner minimization, this is for V, and the solution for V is not unique. Okay, and whenever the solution is not unique, then we know that the outer minimization might be discontinuous. Okay, so then that means we cannot use the, for example, Riemannian gradient method, because it's possible that the objective function in this part about U is discontinuous, so that we cannot compute the gradient. Okay. So one way to address that is proposed by the following works. So for example, this work called the OPT space, okay. And also this work RTRMC by Baumel and Absil. So I will talk about more on this problem because our model is closely related to this model. So this RTRMC denotes for Riemannian trusted region algorithm for matrix completion. Okay. So what they did here is similar to this SET model, but then they add one regularization term here. Okay. So this omega bar, this is also an index set, and this index set is a complement to the index set omega. Okay, so it's like basically I penalize the projection of the low rank matrix onto omega bar. Okay, and this lambda is a positive penalty parameter, and usually lambda is chosen sufficiently small, meaning that we have a very small confidence that those components are close to zero. All right. So after for this model, okay, after I add this regularization term, then for fixed U, then for this minimization problem with respect to V, it admits a unique solution. So that if I solve that variable U in terms of if I solve that problem with respect to V in terms of U, then I got a function with variable U only, and that function is differentiable. So then basically I'm minimizing a smooth function over this Grassmann manifold. Then very naturally I can apply, for example, Riemannian gradient method, or like these authors did in their paper, they can use the Riemannian trust region method. Okay, so these are about the matrix completion problem. Now let's see the non-convex models, the Riemannian models for the Riemannian for the robust matrix completion problem. So for example, this work by Cambier and Absil, they proposed to model this robust matrix completion problem in this way. Here, this part you have a non-smooth function. This is L1 norm. Basically, you are minimizing the L1 norm of the sparse matrix. Okay, so here you can see we are not doing any low rank factorization. So we're dealing with the low rank matrix X directly. Here, this manifold, this is called the fixed rank manifold. So just impose this constraint, the rank of X is equal to R, with R is sufficiently smaller than M and N. Okay. Of course, now for this problem, you cannot use the Riemannian gradient method because the objective function is non-smooth, right? So then these authors they propose that to smooth this L1 norm first using some smoothing technique. Then for the smoothed problem, they can apply the Riemannian conjugate gradient method. All right. So basically, they are not solving this non-smooth problem. Instead, they're solving a smooth approximation to this problem. So another work is done by Laura Balzano and her co-authors. So their approach is called Grassmann. They model this robust matrix competition problem in this way. So as you can see here, basically for the low rank matrix, we're doing a low rank factorization. And then for the objective function, we minimize the L1 norm of the sparse matrix, right? So they proposed this Grassmann algorithm for solving this problem. And this is actually a combination of the alternating minimization method and also the ADMM method. Okay. But as far as I know, so there is no convergence result for this Grassmann algorithm. Okay. Also, very recently, Zhang and Yang, they proposed a different model for this robust matrix competition problem. Here, again, they are using this fixed rank manifold constraint. And this function G here is a hard thresholding procedure. Okay, so basically, this part is about some penalty function about the sparse matrix. Okay, so now let me introduce our model. Basically, we extended this RTRMC model proposed by Baumel and Epsil for solving the matrix competition problem to the robust matrix competition problem. So the difference between the matrix competition problem and the robust matrix competition problem is that here in the robust matrix competition problem, we need to take care of the sparse matrix. Okay, and to promote the sparsity, usually we have a non-smooth objective function. Okay, and then combining with the manifold constraints, this kind of optimization problem can be very challenging in practice. Okay, so now let me propose our model. So our model is given by this. So you can see that basically this part is the same as the RTRMC model for the matrix competition problem. The only difference is here we have a sparse matrix, right? So basically, because we want M, right, to be equal to the low rank matrix plus the sparse matrix, so then we penalize its residual. Okay, and also in the objective function, we add this L1 norm for the sparse matrix to promote its sparsity. Now, as you can see that basically in the objective function, we have a smooth function plus a non-smooth function. And in the constraints, we have a Grassmann manifold constraint, right? So then basically the combination of the non-smooth function and the manifold constraints makes this kind of problem very challenging. Okay. So if we only have one of them, then it's much easier. For example, if we do not have this non-smooth objective function, then we're just minimizing a smooth function over a manifold constraint, right? So then, for example, we can use Riemannian gradient method or Riemannian trust-reaching method. Or if we do not have the manifold constraint, we're only minimizing this smooth function plus the non-smooth function. Then we're actually considering this problem in the Euclidean space. In the Euclidean space, then we know that we have many algorithms for solving this kind of problem. Okay. All right. So then basically, you see this combination of the non-smooth function and the manifold constraint makes this problem very difficult. Okay. Of course, for this kind of problem, you can also use the projected subgradient method. Okay. But since we already have a smooth function here, we don't want to use the subgradient method because we know that, for example, in the Euclidean space, the subgradient method is very slow and it is usually hard to choose the step size. Okay. So a better algorithm in the Euclidean case is this proximal gradient method. Right. Now let me just review this proximal gradient method in the Euclidean setting. we're minimizing a smooth function f plus a non-smooth function h. Then the proximal gradient method can be described in this way. Okay, so in a typical iteration, we just linearize the function, the smooth function f at the current iterate at k, then plus a proximal term. And for the non-smooth function h, we keep it unchanged. Right? So we minimize this function with respect to x to update at k plus 1. Right? And we all know that the solution of this subproblem is corresponding to the proximal mapping of this non-smooth function h. Right? And this algorithm is also known as E-step for solving the compressed sensing problem. In compressed sensing, this function h is equal to the L1 norm. So solving this subproblem corresponds to computing the proximal mapping for the L1 norm. Right? Or equivalently, this proximal gradient method can be written in this way. Right? So at the current iterate xk, right? So we want to compute the step dk by solving this optimization problem. And then we just update xk in this way. All right. So again, this subproblem corresponds to computing the proximal mapping of this non-smooth function h. Okay. So the proximal gradient method can be very efficient if the proximal mapping of the function h can be computed efficiently. All right. So we want to extend this proximal gradient method from the Euclidean case to the manifold setting. All right. So now let me introduce our manifold proximal gradient method. For the Riemannian case, right, for the manifold optimization case, we want to minimize the smooth function f plus a non-smooth function h subject to this manifold constraint. Okay. So basically, the difficulty is that the manifold is no longer a linear space. Okay. Basically, you are minimizing this objective function over a smooth curve. Okay, or a smooth surface. Okay. For example, like the dual principal component pursuit problem that Rene Vidal talked about yesterday, right? So in there, the manifold constraint is on the sphere, right? Or for example, for a lot of models related to PCA, we require the matrix to be orthonormal. Then usually you have orthogonality constraints here in the optimization formulation. So for the orthogonality constraints, it is usually known as the Stiefel manifold, right? Okay, so our manifold proximal gradient method, we call that ManPG. This algorithm can be described in this way. So it is very similar as the proximal gradient method. Okay. However, the difference is that we need to take care of the manifold constraint now, right? So then for the gradient part, for the linearization, instead of using the Euclidean gradient, now we use the Riemannian gradient, right? And also for the direction that we want to move, we need to restrict this direction in the tangent space. Okay, so that's the only difference between this step with the step in the Euclidean proximal gradient method. Okay, and for this subproblem, actually, usually this is not difficult to solve because, for example, if we assume that this function h is a simple convex function, and also this manifold M has some special structure. For example, for the Stiefel manifold, for the sphere, and also for the Grassmann manifold, for all these very common manifolds, this kind of constraint can be written as a linear equality constraint. So overall, this subproblem is a convex subproblem, and it has some very nice structures, and we can use some efficient convex optimization solvers to solve this problem efficiently. After we compute dk, we update xk in this way. So this is another difference between the manifold case and the Euclidean case, because as I mentioned, the manifold is not a linear space. So you cannot just directly add dk to xk, because then your iterator will be outside of the manifold. So this so-called retraction operation actually brings the iterator back to the manifold. Okay, and for this Riemannian gradient, this denoted by this. Okay, actually this is not very difficult to compute. So as Andrew mentioned in his talk, for example, if the manifold is a submanifold embedded in the Euclidean space, and if for this manifold we use the matrix inherited from the Euclidean matrix, then we know that the Riemannian gradient can be computed as the projection of the Euclidean gradient onto the tangent space. Okay. All right. Now let me talk about the convergence results for the ManPG algorithm. So first, let's identify the optimality condition. The optimality condition that is for a feasible X on the manifold constraint, it is a stationary point if this one holds. So this is very similar to minimizing a non-smooth function in the Euclidean space where 0 is a subgradient, right? It's just now here we have a manifold constraint, so now we need to use the Riemannian gradient and also the Riemannian subgradient, right? And we can show that in our algorithm, if the dk is equal to 0, then xk is a stationary point. So then very naturally, we can use this one as the measure for the epsilon stationarity. Okay, so if the size of dk is smaller than epsilon, we claim that we found an epsilon stationary point, xk. All right. Okay, so in this paper, we actually proved the iteration complexity results for the ManPG algorithm. We showed that the ManPG algorithm can find an epsilon stationary point in at most this many iterations. So it is in the order of 1 over epsilon squared. Okay, now let's see how to use this ManPG algorithm to solve our formulation of the robust matrix completion problem. So recall that our model can be written this way. So here we use F bar to denote the smooth function, and we use the blue part, right, to denote the non-smooth function. So here we also have a Grassmann manifold. Okay. So we notice that for fixed U and S, this optimal V of this part, okay, the optimal V is uniquely determined. So if we can represent this solution V using a function of U and S, then we plug that back into this objective function here. We get objective function which only has 2 block variables, U and S. Okay, so then we can reduce this model in this way. So here we have a smooth function about U and S. We have a non-smooth function about S, and we have a Grassmann manifold for the variable U. All right, so then very naturally we can apply the ManPG algorithm to solve this problem. So basically, every iteration we linearize this function f. We compute its gradient with respect to s and also u. Okay, then we add the proximal terms, and if there is a non-smooth function, we keep it unchanged here. Right. So then basically, this is how we update sk. This is how we update uk. And for sk, there is no manifold constraint, so we can just update it directly. And for u, there is a Grassmann manifold, so then we do a retraction step. Okay. And it turns out that these two subproblems, they both can be solved easily. For example, for the delta sk, we notice that there is no constraint. So the solution of this problem just corresponds to the proximal mapping of the L1 norm. And for this subproblem, we see that there is a constraint, but there is no non-smooth term. Okay, so it turns out that the solution of this subproblem is also easy. It is just correspond to computing the Riemannian gradient. Okay, so again, Riemannian gradient can be computed by projecting the Euclidean gradient to the subspace. Sorry, to the tangent space. Okay, now let me give you more details about the ManPG for solving this problem. So in this problem, we have a Grassmann manifold. So for the tangent space of the Grassmann manifold, it can be written in this way. Okay, And then for the projection onto the tangent space, it is not very difficult. It can be computed in this way. And for the retraction, there are many different ways to do retraction. And in other numerical experiments, we use the QR factorization. So this QF denotes the Q factor of this matrix. Okay, so we know that the QR factorization is cheaper than computing the single value decomposition. Okay, so now here I propose a variance of this ManPG algorithm. So basically, we notice that after we update this SK this way, we obtain SK plus 1. Then in the next step, right, when we compute the delta UK, we need to use the latest information of S. So instead of using SK, we use SK plus 1. So in the original ManPG algorithm, this part is SK. So here in this variance, we replace SK by SK plus 1. Okay, and we call this method AManPG. It stands for alternating ManPG algorithm. And we found that in practice, this slight modification can greatly improve the numerical performance of this ManPG algorithm. And in a recent work, we also proved that this AManPG algorithm can also find an epsilon stationary point in this many iterations. Okay, so now I still have a few minutes, so let me just briefly show some numerical results. So this one is about some synthetic data. So we generated the low rank matrix in this way, okay, such that U star and V star, they're both smaller matrices, and their entrants are drawn from a standard normal distribution. And we generated the sparse matrix whose entrants are uniform in this interval. And then we set M equal to L star plus S star, and then we randomly sample its entrants. And we compared our ManPG and AManPG algorithms with some existing methods, for example, the subgradient method, the LMatrix algorithm. And also this one, basically this is about the Riemannian conjugate gradient method for solving a smooth approximation to the problem. In this paper, they call their method RMC. So we just use RMC to denote their algorithm. Now let me explain these results from these two figures. For example, in this figure, we see that the blue curve, that's our AManPG algorithm, and this orange one, that's our ManPG algorithm. So the y-axis, that's the relative error of the low rank matrix, and the x-axis, that's the CPU time. We can see that from this figure, so both our AManPG and ManPG, they're better than the other three methods. And for this one, this is a different instance. We found that our AManPG is still the best one. Now this time the RMC is the second best, and then that's our ManPG, and they're all better than the other two methods. So this is about the random data. We also showed the recovery rate of the algorithms. So this one is our AManPG algorithm. This is our ManPG algorithm. This is RMC. Basically, the white cell here means perfect recovery, and the dark blue means failures. And we found that this AManPG and RMC, they're both better than the ManPG algorithm. But this time we found that the RMC algorithm actually can do better than our AManPG algorithm. Okay, so our AManPG is slightly worse than RMC algorithm. Okay, so we also have some results about the background extraction from surveillance video. So here I only show one example. Here, this is a comparison of the CPU time. Here, this row, we actually sample 50% of the matrix. So this row, we sample 10% entrance of the matrix. And these are CPU time in seconds. We found that our AManPG and ManPG, they're both faster than the other three methods. Okay. And for the, this is the original frame from the surveillance video. This is sampled one. And these are the recovered background using the different algorithm. It's very hard to tell the difference. We only see that this LMatrix algorithm has some artifacts. Okay. So then to better illustrate the difference, we use this so-called D epsilon matrix. to compare the quality of the recovered background. So basically here, this function is defined in this way. We have a tolerance epsilon. If these two components, their difference is smaller than epsilon, then we set this b epsilon equal to 1. Otherwise, it's equal to 0. So basically, we want this one to be as close to 1 as possible. And we found that the same as what we observed from the figure. So this L method is the worst one, and the other 4 methods, they have very similar performance. Okay, so now let me just briefly conclude. Basically, in this work, we give a new non-convex model of the robust matrix completion problem. Our model is a Riemannian optimization problem with non-smooth objective function. So usually this kind of optimization problem is very challenging to solve. In this work, we proposed this manifold proximal gradient method to solve this kind of problem. Basically, this is an extension of the proximal gradient method from the Euclidean space to the manifold optimization setting. We also proposed a variance of the MAN-PG algorithm. This is the alternating MAN-PG algorithm, which works very good for this robust matrix completion problem. We also analyzed the iteration complexity results for both methods, and we showed some numerical results to compare with existing works. And with that, I conclude my talk. Thank you very much.
Great. Thank you so much for this very comprehensive and interesting talk. Any questions or comments from the audience?
Can I have a question?
Yeah. Mm-hmm. Yeah, please go ahead. Yes, it's you.
Thank you. On the previous slide, what is the difference between these two graphs? On slide number 8.
This one? Okay,
yeah,
so
yeah.
This is just for different for 2 different instances, for two different problems. Yeah, sorry, I didn't mention that. Yeah.
Okay, yeah, thank you.
Let me ask one more thing. Did you find any significant difference in which stationary points you're converging to between the different algorithms, or pretty much they all converge to the same thing?
Oh, actually, we found that they usually they converge to the same solution. I think probably that's because the problems that we tested were relatively easy.
I see. Any other questions or comments? Good. Then we'll move on to the last speaker of the day, which is Daniel Berth.